This is Math 251, and we're in Section 14.2, Part B. What we've seen so far is a process that allowed us to integrate a function along a curved path. But the integrands that we've used so far have always been scalar functions. In this next part, we're going to look at doing these line integrals. In other words, we're still integrating along a curve. Again, weird name, I know. Line integral for integrating along a curve, but such is what it is. But this time, our integrand is going to be a vector field. Think of it as F, our vector fields. We're going to begin this process by looking at an application to the physics concept of work, because it does a really good job of explaining why it is that we use the process that we do to do these integrals, and then we'll generalize from there. So I'd like to go back and take just a few minutes to review the ideas of finding work done by a force that you've seen so far. Back in algebra, we just simply had the equation work is equal to force times distance. What this assumed was that if you were moving an object from one position to another, the force was some constant, and scalar. It assumed that the distance was all along a straight line, so straight line motion. And it also assumed that the force was in the same direction as the motion. So I'm just going to say F and D, same direction. And let's see, I'm going to say straight line motion D. So from here to here is our D, and this is our scalar value of the force F. All right, in mostly Calc 2, really, we talked about what happens if the force is variable. These were those problems like the leaky bucket problems, where sand leaked out of the bucket, so the weight or force of your object varied over time. And when that happened, we did allow for variable forces, and that meant that we had to do our work as an integral. We usually looked at it this way. A to B here. So F can vary, but it's still a scalar quantity, right? When you thought about those leaky bucket problems, the weight of the bucket was still a scalar. It was just a number. We still had straight line motion. The bucket was either lifted straight up or lowered straight down. And F and D are still in the same direction. Since the bucket was always raised or lowered, that's the same direction that gravity acts, vertically. So F and D are still in the same direction. All right. Finally, we're going to be getting to this semester, the beginning of the semester, we were able to relax another restriction, right? We were able to relax the idea of F and D having to be in the same direction. We now defined our work to be the dot product of two vectors, F dot D. F was back to being constant, but now it was a vector. We still had straight line motion, but the vector F and the distance vector D did not have to be in the same direction. This was the sort of a situation where perhaps the force was applied at an angle to move our object, for example, along a horizontal. so they didn't necessarily run in the same direction. So far, we've dealt with issues where the force can vary. We've dealt with times where F and D were not in the same direction. But notice the one thing that stayed the same every single time. We always had to have this straight line motion. No matter what, we were never able to get away from that. That's what we're going to concentrate on now. We're going to say, what if we want to move the object along a curved path? We're set up really well to talk about that, since we've just been talking about curved paths and how to integrate along them. Notice that this is probably going to give me the most general situation yet. I'll be able to have a variable force, since I now know how to integrate on a curved path. And again, because I have a curved path, I've relaxed that straight line motion. And since I'm not even moving in a straight line, certainly F and D will not be in the same direction. So I'm going to be able to generalize completely a variable force and a curved path. Let's take a look. I'm going to assume that I'd like to move my object from some starting point P to some ending point Q along this curved path C. Furthermore, I'm going to, well, let's start with that. Path is the curve. C, which, as is typical, we'll normally parameterize that as R of t for t values between some A and some B, which give us our points P and Q. All right, that takes care of the curved path. I would like to allow for a variable force, like we did up here, right? We want a variable force. And the way to get a variable force is to put this curved path in a vector field. If I've got a vector field out here, I'm just going to kind of randomly draw some vectors. If this is some vector field out here, then I've got a variable f. A vector field. F of t. Now notice it's definitely going to be true that the force will not always be in the same direction as the motion. In fact, if we just pick a point here, let's go with this one right here where I happen to draw a vector right on the curve. The force points this way, but the direction is that way. So we'll certainly notice that F is not in the same direction as the motion. As a matter of fact, I'm going to take this little section right in here and I'm going to enlarge it. Let's suppose that I want to think about right at that specific point, I've got one vector from my vector field acting. And I can imagine that that's valid for some little distance along the curve. So I'm going to assume for this small distance, ds, I've got this one specific vector f. And I'm going to enlarge that little piece down here so we can talk about it a bit more. So let's say that I've got my little piece of curve ds. And I've got my vector f here that acts right at that endpoint. And we'll assume that that vector is valid for that whole little piece of the curve. As you've seen so many times, ultimately we'll shrink that ds down to differential or infinitesimally small size, so that assumption will be valid in that infinitesimal case. All right, because f is not in the same direction as the motion, we've seen in the past that the only thing that counts for the work is the part of f that acts in the direction of motion. The direction of motion for this little piece can be considered to be the direction of the tangent vector. So I'm going to sketch in the unit tangent vector, capital T here. And if I project my vector f down onto that unit tangent, then this is the only part that counts when I'm doing work. It's the part of f in the direction of motion, direction of t. The tangent represents the motion at that instant. All right, well, let's see here. If I think of this in terms of this angle theta, let's just go ahead and say this angle in here is theta. Then this would be the x component with respect to theta. So I'm going to say f with respect to its x component only, we know is way back to chapter 11 now, the magnitude of f times the cosine of theta, right? The y component would be the magnitude times the sine of theta. Again, thinking way back to the beginning of this semester. All right, I'm going to use a little cheat here. I'm going to throw in an extra factor of magnitude t. Why can I do that? Well, remember, t is the unit tangent. So what's the magnitude of any unit vector? Just 1. So all I've really done is put in a multiplier of 1, which of course doesn't change the value of this at all. But what it does do is hopefully make this something that you recognize. That's just the dot product, isn't it? The dot product of f and t. So the force that I want for this little tiny piece is F dot T. The distance that I want for this little tiny piece is my distance ds here. And so the work, force times distance, is F dot T for the force times ds for the distance. And that will give me just this one little part of the work. If I want all of the work as I go from P to Q, I'm going to have to integrate this over the entire length of the curve that I want from time A to time B. All right, not bad. It's a good start. Now, let's do a little bit more. We also know that this is not a great integral to evaluate. We saw this before, because we don't like to integrate ds. Our curves are usually given with respect to time parameterizations, not distance ds. So let's work on this a little bit more. The unit tangent vector. Well, to get the unit tangent, right, it's tangent, so it's the derivative, r prime. But to make it a unit vector, we divide it by its own magnitude, the magnitude of r prime. So there's just an expression for t. And then ds, remember this one from the previous section, right? We know that ds dt is speed, and the magnitude of r prime is also speed. So remember that ds was magnitude of r prime dt. I'm going to use that again. So, really nice something happening here, right? The magnitude of r prime just cancels out. And I end up with just getting f dot r prime dt. And that is actually the most convenient form that we can work with when we want to find the work over a variable force over a curved path represented by r. All right, that's summarized for us in the next page, and we'll look at a couple of examples. By the way, in this box, there's one other kind of important thing here. This is just an alternative notation. You'll see it a lot. Sometimes instead of writing out f dot r prime dt, we sort of abbreviate with f dot dr. And we actually saw another one, right? We also saw f dot t ds. All three of those, as well as one more that I'll be showing you in a little bit, are legitimate ways to write the line integral on a vector field. So f dot tds could be written as f dot dr, but when you actually want to evaluate, when you want to do the math, this is by far the most convenient form, because this one actually tells me how to do the evaluation. So that's the one I'll use, even if the problem asks me in one of these ways. This will always measure the work done in moving an object along the path C through the vector field F. Okay, so in number 4, we'd like to find the work done in moving an object along the line from the point 1, 2, 1 to the point 2, 4, 6. And we're doing this in the radial vector field x, y, z. So I'm going to start, like I've always done in the past, by coming up with a parameterization. I need the r. I've got my 2 points, so to get a line between 2 points, I need a direction vector, v, which I'll get by subtracting terminal minus initial. It's like 1, 2, 5. I need a point, which I'll turn into a vector, OP. I'll just use the first one, 1, 2, 1. And therefore r is going to be t times that direction vector added to the point vector. So I have t plus 1, 2t plus 2, and 5t plus 1. All right, I need a couple of things that I can get from r. I need r prime, and I need f. So I'm just going to go ahead and make this kind of my laundry list of everything that I'm going to need for my integral. R prime, the derivative is easy enough to get. 1, 2, and 5. And then f, in this case, is just x, y, z. So that's simple enough. When I defined r, I automatically defined an x, a y, and a z. And I'm literally going to plug that x, y, z into the f formula. Now in this case, the f formula is extremely simple. We'll see ones that are a little bit more involved later on. But in this case, plugging x in here, I just get t plus 1. And of course, the second component is still y. And the third component is still z. That gives me both the f and the r prime, which is what I'm going to need to plug in to evaluate my integral. One last thing, I have not yet written down an interval to integrate over. And again, when I do a line by just subtracting the 2 points to get v, and I don't change v at all, automatically my t values will work if I just let t go from 0 to 1. So I'm good enough to go here. I'm ready to set up my integral. The work, the integral from a to b of f dot r prime dt will be the integral from 0 to 1 of this vector field f dot product with the r prime dt. So I'm going to get 1 times t plus 1 plus 2 times t plus 2t plus 2 plus 5 times 5t plus 1. And you can do the algebra first if you want to, or you can just plug it into the calculator the way it is. I got 25 when I did that. And that would be in the units of work. Foot pounds, Newton meters, whatever it is. I didn't give us units, but just as a reminder, since it's work, this would be something like Newton meters or foot pounds or whatever. All right, let's go ahead and pause there, and we'll come back and talk about a little bit more general form or application of line integrals in the next video.